This is level 2 of the CFA program, the topic on fixed income, and the reading on valuation and analysis of bonds with embedded options. This reading could be called, we've already done this, but now we're going to apply the arbitrage-free valuation model from our previous reading to embedded options. Notice I said it could be called that. Let me show you what I mean in these LOSs. Look at those first handful there. Describe fixed income securities. We did that in the last reading, but now we need to worry about embedded options. So those are callables and putable bonds. Look at that third one. There's the arbitrage-free framework, and then we talked about interest rate volatility and then level and shape of the yield curve. So those first handful are going to provide us with the foundation in order that we can succeed in applying that framework to bonds with embedded options. But then we're going to add a substantial amount of information: option adjusted spreads, effective duration, key rate duration, convexities, convertible bonds, floating rate bonds. So this is a super long reading, and we have a super long slide deck prepared for you. So I will do my best to keep this as short as possible without sacrificing attention to lots of the details that hopefully you're used to. All right, let's start with a brief recap. What we've talked about in some of the previous readings are option-free bonds, just like a regular bond, where the issuer, whether it's the government or a corporation, makes an explicit promise that sounds something like, hey, I'll pay you interest in principal over 10 years or 20 years or 30 years. Bonds with embedded options have an extra kind of a promise in there. And the promise is, hey, I'll pay you interest and principal for as long as I feel like it, right? I might decide to buy those bonds back from you if, of course, it's beneficial to me. And then on the other hand, you may force me to buy those bonds back from you if it's beneficial for you. So there's the call and there's the put. And there are also some conversion provisions in there that allow a bondholder to convert a bond into a share of stock. And then notice the bottom right there, there are caps. Issuers like to use floating rate bonds because they expect interest rates to either stay the same or fall. And it's common to go ahead and put a cap on it so that you can't pay a coupon higher than some number, or it's common to put a floor on there as well. So there's some good examples of embedded options. Look at that third circle point there, complicated to value. So let's go ahead and try to decomplicate the process. I'm not sure if that's a word. First LOS, describe fixed income securities with embedded options. All right, let's start with a call option. So what do we know? A call option gives the owner the right, but not the obligation, to buy the underlying asset at a fixed price over a specified time period. So a callable bond is a bond that is known as a bond with an embedded option because it has a call option embedded inside of it. So look at that first circle point, can be redeemed before maturity at the discretion of the issuer. Now, most of these callable bonds have a deferred period. So if a company issues a bond that matures in 30 years, there might be a lockout period of 5 years or 8 years or 12 years, under which that first time period, the bond cannot be called. Callable bonds can have a couple of varieties: European, American, and Bermudian. I think the Bermudian adds some interesting complications to it. Can only be exercised at predetermined rates. Put option, on the other hand, is embedded into a bond that gives the bondholder the right but not the obligation to put the bond back to the issuer before expiration. And of course, it has a lockout period as well. No American putable bonds are out there. And then look at that last double circle point there at the bottom. there are some bonds that allow the bondholder to extend the bond's maturity from, let's say 30 years to 35 years. So think about, a put option or a call option that has an extension option in there. That's kind of a double derivative. There's a section in the reading on some additional complex bonds with embedded options. And here are just a couple of examples. A convertible bond, I talked about that. Callable plus putable, so you got it on both sides. And the interesting thing about that is that the options are not symmetric. So it's not like those two things exactly cancel each other out. And you should be saying, oh, Jim, you didn't need to tell us that. We remember that from those pictures back in level 1 of a call option and a put option. How about an estate put? This is a bond that's contingent upon the death of the investor. So if you can provide a death certificate, then you can put the bonds back to the issuer. And then lots of bonds have sinking funds, primarily because the sinking fund then reduces the likelihood of default on the bond. And so there are all sorts of delivery options in those. So I think knowing just about those 4 types of extra complexified bonds with embedded options, I think that handles that part of the described fixed income securities with embedded options. All right, so let's go ahead and try to match what we know from before, an option-free bond, with bonds that have embedded options. So let's start with an embedded call option. All right, you ready for this? A callable bond is similar to a portfolio. I love this. This is why I tell my students that the study of derivative contracts and derivative securities is so valuable, because essentially what we're doing is we're just forming a portfolio with a regular old bond, option-free bond, and a call option. So long position on a straight bond and a short position on the call option. And so look at the box down there at the bottom. The value of a callable bond is equal to the value of a straight bond, option-free bond, minus the value of the call. So bonds with embedded call options will sell for lower prices than identical bonds that have no option embedded in them, because of that short position, right? That short position lowers the price of the bond. Here's a great illustration. This picture is taken out of every single investments in derivative securities textbook that's out there. And so notice the black curved line. There's an option-free bond. Value of the bond on the vertical axis, yield to maturity on the horizontal axis. And so, of course, it's downward sloping, right? We know this from level 1. And I'm guessing you know this from your undergraduate days. Maybe you even learned it back in high school, that as the yield to maturity on a bond increases, the price of that bond decreases. So there's that downward slope. But notice that it's not a line. So there's a curve to it. And that curve is called convexity. And so at high yields, at higher yields to maturity, an option-free bond and a callable bond have pretty much the identical yield-price relationship. That's called the positive convexity. So look to the right of that red dotted vertical line. That's like regular old bond yield relationships that we talked about back in level 1. However, we have to ask ourselves the question, when are issuers going to call a bond? Why do they do this? Well, of course, the answer is when interest rates fall, the issuer doesn't want to continue to have to pay the higher coupon rate. I mean, imagine a bond that has a coupon rate of 10% and yields fall down to 3 or 4%. Well, the bondholders, they're delighted to get their 10% coupons, but the issuer is going to say, wait a minute, I can issue another bond at a 3 or 4% coupon, take the proceeds, and repurchase all those 10% coupon paying bonds. And so that's what happens there at that point of inflection. With an option-free bond, that price is still going to go way up, right? If yields fall down to 3 or 4%, that price might be $1,100 or $1,200. on the option-free bond. But since there is a call feature in this bond, it's going to turn from positive convexity to negative convexity, and that's that dotted line. We call that negative convexity. Not quite sure why we don't call that concavity, but either way. And so notice the difference between the dotted dark blue negative convexity that reflects the callable bond price yield relationship. That difference between that dotted line and our original first black curved line, that's the value of the call. Let's go ahead and switch over to an embedded put option. And this illustration is identical to the previous illustration, but it's turned upside down, right? When does the value of the put increase? That's when interest rates rise. So you get more positive convexity at higher yields. So there's the option-free bond, our regular old black curved line. But for a putable bond, when yields go way up, then the value of that putable bond will increase, so it has more of a positive convexity, right? So let me toggle back and forth here, right? What's the worst news for a callable bond holder? That yields are going to fall and that price is kind of maximized at its par value, let's say, maybe plus a coupon payment. How about down here? For the issuer, the worst thing that can happen is that interest rates rise and then they're forced to buy the bonds back from the bondholders at a higher price than that of the option-free bond. And so I wouldn't be surprised if I were creating exams. I wouldn't be surprised to see something like this, an actual picture and an actual picture, although I don't think the Institute historically has drawn pictures for you on exams. But I think these are great sources of exam questions. How about this LOS that sounds almost identical to what we did in that previous chapter, with the exception of this LOS in this reading has the word embedded in it. So we're going to use this same process that we did in the previous reading. Notice there's the binomial interest rate tree framework applies here. All right, so there's some curves. There's the spot rate curve, and then you can, excuse me, you can go ahead and do the math to compute those 1-year forward rates, 1.2, 3.44, 5.45%. But assuming that those are correct, let's go ahead and consider a 5% annual coupon paying bond. You know, the annual part there, that just kind of makes the calculations just a little simpler. That matures in 3 years. And then let's go ahead and consider both the callable bond and then the putable bond. And in order to compute those, we're going to need the value of a straight bond, just because of that relationship there. Up in the box, right, value of the put is equal to the value of the putable bond minus the value of the straight bond. And then back here we have something similar to the value of the call. So we're going to use those equations to go ahead and help us compute the value of the callable and the putable bonds. Now what I want to do here is just take you through the math, not too quickly, but not too slowly as well. We have an example later on where we're going to show you the exact tree and how we make these decisions at each node. But we thought it would be better for us to start with just some math here. So think about this process of backward induction, right? We're going to start all the way at the end. So we've got this bond. Let's go back here. 5% annual coupon matures in 3 years. So par value of 100. So in year 3, we're going to get the 100 and we're going to get the 5, right? So there in the numerator is that 105 final cash flow. in year 3. So what we're trying to do is value it in year 2. So there's the V sub 2 callable in time period 2. So we just discount it at that, wait a minute, let me go back here, discounted at that future 1 year forward rate, 5.45, and we get 99.57. So now at this node, and this is where it becomes a little bit more complex than what we did back in the previous reading, is that we have to decide, okay, is this bond going to be called at that price or not? In other words, what do we know? We know that when interest rates go up, bond prices go down. When interest rates go down, bond prices go up. If interest rates fall far enough, then in fact we'll go ahead and call the bond. But here, since we're discounting at that 5.45, we're going to get 99.57, which is less than 100 par value. So look at that first circle point. This is important. Therefore, the bond is not called in year 2. So we're going to leave that 99.57 at the node in year 2. So next step then is to discount that 99.57 plus the extra $5 coupon payment, and we're going to discount that back at the, now wait a minute, let's go back here and look at the 1 year forward rate in 2 years at 3.44. So we get the 101.09. That's the value at time period 1 of the callable bond. Now, wait a minute. What are we saying? Interest rates are falling, right? 545 down to 344. The question is, have interest rates fallen enough for us to call the bond? And the answer is yes. 101.09 is greater than 100. So at that node, the investor will only receive the $100, not the 101.09 like we did back in the previous reading. So the final step then is to say, okay, the value today, value time period 0, the callable bond, is the call amount plus that coupon payment of $5 divided by, well, what are we discounting it to? Discounting it by, well, we discount it by the 1 year forward rate, but that of course happens to be exactly equal to the spot rate, so 1.012. So that gives us the value of the callable bond, 103.75. Backward induction, exactly like we did in the previous reading. However, we need to sometimes cross out the bond price and substitute it with the lower $100 par value. Now we're going to do the same thing here with the putable bond, but remember, we need to turn our thought process upside down. So let's do that very first value in time period 2 of the putable bond. We still have the 105, right? The 100 plus the $5 in coupon divided by that, well, here, let me go back again, divided by that 5.45% forward rate that we're using as the discount rate, and we get, well, we're going to get that same 99.57. But now the put option will be exercised in year 2 because it is less, that future value of the bond is less than the $100. So we're going to cross out the 99.57 and substitute the 100 in there. So we're continuing our backward inducting value at time period 1 of the putable bond. Notice there's the 100 in the numerator, so that's the par value plus the $5 divided by that relevant forward rate. We get the 101.51. That's greater than the 100 par value, so put option will not be exercised. So look at the very bottom equation, value of time period 0. There's the 101.51 because the put option will not be exercised, plus the $5 in par value. Discounted at that first forward rate, which is the spot rate, of course. So you get the 105.25. You ready for this? So let me go back. So callable bond, 103.75. Putable bond, 105.25. We've done that just like we did all the way back when we first learned how to price a bond, right? The value of a bond is the present value of the promised payments. But with an embedded option, that promise takes on a little bit of a unique characteristic. That promise depends on the interest rate path. And so sometimes we get the market value of the bond, or at least the theoretical value of the bond. Sometimes we get par value. All right, so let's go ahead and do the third step, the value of the straight bond. We're just going to discount those back. That's simple backward induction that we did in the previous reading, and we get the 104.83 for the option-free bond. And then we can use those two equations that I showed you from those previous slides, and they're repeated here. Value of the call, what is that? $1.08. Value of the put, 42 cents. Now notice that this LOS asks us just to describe how this framework can be used to value. And of course, you should know this by now that we love providing you with some mathematical examples so that you can, in fact, go ahead and do the math and then use that mathematical foundation to describe. Now, of course, a later LOS is going to say, hey, let's go ahead and not just describe, let's go ahead and calculate as well. We'll do that in just a few minutes. But here, to answer this LOS, describe, all we're doing is computing present value and using that backward induction with the interest rate paths that depend on whether the bond is called or whether the bond is put, depending on if it's a callable or a putable bond, will influence the value of those bonds with embedded options. And so then you back into the value of the call option and the value of the put option. But I think to emphasize this here again, it's worth repeating. When we describe this, you talk about the interest rate tree, talk about backward induction, talk about the interest rate path, but really the bottom line is we're still computing bond price as a present value. All right, how about interest rate volatility? Boy, what do we know about volatility and options from level 1? And of course, we'll expand on this as we move through the readings in level 2, is that, oh boy, if you buy a call option on a company like the Pennsylvania Water Company, what do you know? The Pennsylvania Water Company's stock price, goes like this, because there's lots of regulation and water consumption is fairly predictable. Compare that to a call option written on Amazon stock. What does Amazon stock price do? It goes way up and way down, although, it pretty much just goes way up over time. But still, what do you know about those call options? You're probably not going to pay much for a Pennsylvania Water Company call option because it doesn't have much volatility. You're probably going to be willing to pay lots for a call option on Amazon stock because it has lots of volatility. Well, of course, those principles apply to bonds with embedded options. So look at that first double circle point. The value of embedded options increases with interest rate volatility. Makes perfect sense, right? So higher chance of being exercised when volatility is high. So let's go ahead and differentiate between a callable bond and a putable bond. So let me read these to you. That first double circle point. As the interest rate volatility increases, the value of the call option increase, and that must mean that the value of the callable bond increases. That makes perfect sense, right? Based on our understanding of call options and our understanding of straight bonds, and now our understanding of callable bonds. Let's go ahead and do this with the put option. The value of the put option will increase with an increase in interest rate volatility, implies the value of the putable bond also increases. Now, notice I didn't read this back in the last slide. Let me go back here. The value of the straight bond remains unchanged. For the callable, the value of the straight bond remains unchanged as well for the putable. So that's kind of a pretty important assumption here as you go through explaining how interest rate volatility affects the value of the callable or the putable bonds. All right, remember in that last reading we had a couple of effects, 3 of them I believe. So let's do the level effect. We know this. As interest rates fall, value of the straight bond increases. However, part of this increase is going to be offset by the increase in the value of the call options, which means, and this is really important, look at that third double circle point, the value of the callable bonds rises less quickly than the value of the straight bond. And this puts a ceiling on the investor's upside potential. And let me just go way, 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 way back here. That's what that negative convexity is as it curves over this way over to the vertical axis. Think of that as the ceiling on the bond. Let me make sure I get back to the yeah, there we go, the bottom blue point puts a ceiling on the investor's upside potential. Now, how about the shape of the yield curve? All right, so what have we learned? Wouldn't life be so much easier if we always had parallel shifts of the yield curve upward or parallel shifts of the yield curve downward? Wouldn't it be awesome if we didn't have twisting and curving and humping and all that kind of stuff in there? But of course, we know that that's not the case. All right, so as the yield curve shifts from an upward slope to flat to inverted, now this is super important. Value of the call option is going to increase. You think about it, from upward sloping to flat to inverted. So that's just an illustration that interest rates are falling. So call option increases, which means the value of the callable bond decreases. In an upward sloping yield curve, what this means then that those forward rates, are probably going to be higher. Remember, the spot curve looks like this, and the forward curve looks like this, right? It's above it. So that's going to provide us for decreasing the opportunities to call the bond because interest rates are expected to rise, right? But when the yield curve flattens, or if it shifts to being downward sloping, then there's an increase in the chance that the bond will be called. And all of these double circle points and single circle points on this slide, they all are based on the well-established knowledge that we all have that, of course, when interest rates fall, the bond is probably going to be called. So now what we've done here, explain how, right? Explain. So now we look at the shape of the yield curve and just decide how that affects interest rates, and that will help you answer whether the callable bond is more or less likely to be called. All right, we can quickly summarize the putable bond here after I spent all that time on the callable bond. So for the level effect for the putable bond, as interest rates increase, value of the straight bond falls, right? We know this. But this is partially offset by the increase in the value of the put option. So look at that third circle point. The value of the putable bond falls less rapidly than the value of the straight bond. So what did we have right back here? Callable bond rises less quickly. Putable bond falls less quickly. All right, so those are probably two really important statements to memorize so that when you get to the question stem and you're reading the vignette, somebody inside of that vignette is going to make a comment. And that comment is going to be one of those two sentences. You'll either have to agree or disagree with it. And then as for the shape of the yield curve, the value of the put option declines as the yield curve shifts from sloping upwards to flat or inverted. That makes sense. All right, you ready for this one here? If you can do this LOS, calculate the value, then I think all of those other ones fall in line, which is something similar that I said to you in that last reading. But here, you already know how to do this, right? We talked about this in the last reading. We talked about this briefly at the beginning of this slide deck. All right, generate an interest rate tree, doing all the stuff that we did in the last reading. Determine if the embedded option will be exercised at each node of the tree. So this is the important difference between what we did in the previous reading and what we're doing now. We have to make a decision at each node. Is the call going to be exercised? Is the put going to be exercised? If the answer is yes, we cross out that theoretical value and put in 100. And then the third one here, gosh, I've been emphasizing this all along. Calculate the present value using backward induction. All right, so let's go ahead and work through an example here. All right, here's some interest rate tree that has been calibrated. So remember, we did that calibration back in the previous reading. And so the spot rate is 1.5. So how do we get that 2.5% at time period 1? Remember from that previous reading, the author suggests, hey, let's just go ahead and guess at it and then go ahead and do the math and see if it's right. But the guessing you really don't have to do. You put it into some algorithm and use simultaneous equations and figure that one out. So I'm pretty certain that on the exam, you will be given a calibrated interest rate tree. So look down at the bottom. What are we doing here? We have a 3-year default-free 5% annual coupon bond, callable at par 1 year and 2 years from today. So let's go ahead and figure out how we work through this backward induction, how we cross off some market values or theoretical values, and we continue to take present values. Now, what we've done for you is we've put together this slide, and I have this duplicated in 3 or 4 slides below. So let's not worry about the math here, but I want to show you exactly what you're doing in this process. So look out at time period 3. There's the 5% coupon, right? So there's the $5 and there's the par value 100. So that's the same out in time period 3, which is the maturity date of the bond. So we take present values, we're backwardly inducting. We take present values using those rates given to us in the tree, 6.5, 5.5, and 3.5, and we get a value. We get 98.59, 99.53, 101.45. So we have to ask ourselves at each node, will this bond be called? And of course, the answer to that question is, well, it depends on its relationship to the $100 par value. So at those first 2 upper nodes, 98 and 99, they're both less than 100, so they're not going to be called. But look down at the bottom node in time period 2, 101.45. Notice that we've drawn a line through that. So there's the crossing out. It's going to be called at 100. So when we continue to backward induct, we're going to use the 100 to get the present value at each time. And so we work our way all the way back to get the 103. So there's part of the previous LOS, describe the process. And let's go ahead and view the calculator steps to do the actual math so that we can calculate. So I have that, we have that written on the next couple of slides. All right, so there's the value at time period 2 for each of those nodes, right? UU, UD, and DD. So there's the 105 in the numerator, and we're discounting those back at those rates that are given to us in the interest rate tree, 6.5%, 5.5%, 3.5%, and we get the 98, the 99, and the 101. All right, so that's how we computed those values right there, 98, 99, and the 101. So now we have to go down to that diamond point. Oh, let's ask ourselves the question, is the bond going to be called at each one of these nodes? Well, it's no for the first 2, but it's yes for the third one. So that bond is going to be called during that interest rate, that specific interest rate path. So what do we do here? We've got to use that 100 par value and substitute that in for the 101. So continuing to take the present value, so the value at time period 1 using that upper node, we're just going to take half of the 98, half of the 99. Of course, don't forget to add the coupon payment in there. Discount that at the rate given to us at the at that second time period. Take half of it, take half of all of that, right? And you get the 99.10. And then, of course, we do this at the down node, value at time period 1 under the down. So we do the same thing, but notice that instead of entering, here, let me go back here real quickly. Instead of entering that 101.45, we enter the 100 plus the 5, because during that interest rate path, that this bond will be called. So you take half of those two. Remember, you're taking half just because you're taking an average of the present values. Remember, we're assuming that we have a 50% chance of going up and a 50% chance of going this way. So let's once again ask ourselves the question, is the bond going to be called at 99.10? No way it's going to be called then, because that's less than 100. But at 102.21, of course it's going to be called. So we scratch off the 102 and we substitute the 100 in there. And lo and behold, there's the 103. So let me just show you this slide again. I told you I had this duplicated. So here we go. We're backwardly inducting, and we scratch off the 101.45 because it's going to be called. We scratch off the 102.21 because it's going to be called. So backward induction with the interest rate tree. Ready for this? Considering the possibility that this bond will be called, there's a good old market value of 103, because remember, the interest rate tree was calibrated, so we're pretty confident in that 103 value of a callable bond. How super cool was that? All right, let's move on to the concept of spreads. We've talked about spreads back in level 1. We'll talk about them extensively in level 2, and then a little bit more in level 3. But remember, a spread is just the difference between two rates. Well, of course, when we're spending all this time on callable bonds and putable bonds, we have to ask ourselves the question, is there a spread that's relevant for bonds that have embedded options? And of course the answer is yes, option adjusted spread. So this is the fixed spread added to the 1-year forward rates on that interest rate tree that equates the arbitrage-free value and the market price of the bond that has an embedded option. So I always think of it like this. I use this for my students. I say, look, you have this theoretical arbitrage-free value, and you have the market price over here, right? So you want to clash those two. You want to force them to be the same dollar amount, and the only way to do that, because we have these embedded options, is to add this option-adjusted spread. Now, we have talked about the Z-spread. For an option-free bond is its option-adjusted spread, assuming volatility of 0. All right, so look at the option-adjusted spread is the Z-spread minus the option cost. And there's a pretty good illustration down on the bottom left. There's the big old Z-spread. You know, there's the big arrow up and down, and then you can divide that into its two components, the cost of the option and then the option adjusted spread. Now look at the arrow points over on the right. Two bonds with identical characteristics and credit quality, they ought to have the same option adjusted spread. However, sometimes they don't. Bonds with larger option adjusted spreads are probably going to be undervalued, so we want to find those kinds of bonds. Here's just a really quick, super simple example here. We got two bonds. They're risky. They've got identical characteristics. Which one is most likely to be underpriced? So bond X has an option adjusted spread of 30 basis points, bond Y 20 basis points. So X is going to be underpriced because it has the larger option adjusted spread. All right, let's continue on this kind of a conversation about volatility, but let's apply it to the option adjusted spread. All right, look at that second teardrop point, the indented one. For a callable bond, the option adjusted spread decreases as interest rate volatility increases. Okay. Oh, let me take a deep breath and repeat that. So we've got to worry about this. When interest rate volatility increases, so if standard deviation goes from 10 to 20%, then that option adjusted spread is going to decrease. And that's, of course, based on all the relationships that we've described over the previous couple of slides. A high volatility assumption generates a higher value for a call option. We know that. So look down at the bottom in that gray box, value of a callable bond. We know it's equal to the value of a straight bond minus the value of the call option. So what we need to say is when the volatility increases, right, the value of that callable bond, oh my gosh, and then let's go all the way over to the far right, that option adjusted spread. So volatility goes up, option adjusted spread goes down. And of course, what we're going to do for the putable bonds is we're going to kind of halfway turn on our head here, because what's going to happen is that the option adjusted spread of the putable bond is going to increase as the interest rate volatility increases. All right, moving on to interest rate risk. This is an important concept in fixed income valuation and fixed income portfolio management. We know that when yields go up, bond prices fall, but the question then becomes by how much? And we know from previous discussions that duration is an important measure of interest rate risk, as is convexity. And of course, I showed you that on those dotted curves about the importance of convexity. Let me go ahead and give you a little bit of calculus background here. We're looking at the price-yield relationship. Duration is going to be the first derivative. That's why duration oftentimes is called a measure of sensitivity. Oh my gosh, there's the word sensitivity on the slide. And then convexity is the second derivative. This is why the CFA Institute makes you take a couple of readings on micro and macroeconomics back in level 1, and then of course extensions of that in level 2 and level 3, so that you understand when someone says to you, oh, that variable is increasing at a decreasing rate. So convexity, second derivative, tells us about that. But let's go ahead and focus on duration here. We'll come back to convexity in just a little bit. Now remember, we did regular old duration and Macaulay duration and maybe some other kinds of durations for option-free bonds. Well, we need to make an adjustment. We call this the effective duration. Some people call it the option-adjusted duration. And this is way more appropriate measure for bonds with embedded options because, the duration of a 30-year option-free bond is going to be, let's say 12 or 14 years, depending on those input variables. But a 30-year callable bond ought to have much less duration because it can be called in year 5 or 7 or whatever it is. And so, boy, there's where it's truncated, whereas you don't have that scenario with an option-free bond. So look at the second teardrop point. Duration is the sensitivity of a bond's price to a 1% parallel, oh, there we go again, parallel shift in the benchmark yield curve. So there's a good old formula that you ought to memorize for the exam. Calculate and interpret the effective duration. And so all we're going to do in the numerator is say, hey, what happens if the parallel shifts by 100 basis points up, what's the bond price? How about if 100 basis points down, what's the bond price? So it's the difference in estimated bond prices in the numerator based on a 1% increase or decrease in the yield curve. And then, of course, we need to standardize that. So we're going to divide it by 2 times the original price of the bond with the embedded option times the change in the yield curve. All right, so let's go ahead and work through an example here. Here are the steps, right? Determine the implied OAS to the benchmark, right? Shift the benchmark curve up or down, and then calculate the new price for both the up or down, and then do the effective duration of the bond. And so this example that we have for you here is super, super simple, but I think it's pretty relevant. Ready? All right, 3-year bond, 9% annual coupon, callable, currently priced at 105 with some assumed interest rate volatility. All right, so you ready for that second sentence there? This is the simple one. If the benchmark spot curve shifted up by 30 basis points, the price falls to 103.48. If the benchmark spot curve is shifted down by 30 basis points, the price remains at 105. All right, so there are those two prices. So go back here. So step 2 and 3, those sound like super difficult steps. However, they're not, especially in this case, if they're given to you. But if they're not given to you, then you have to go through that entire process that we just did with all of the backward induction and the interest rate tree. But my guess here is that you're going to be given the 103.48 and the 105. And so you just use that formula there. So 105 minus 103, what's that? That's about $1.50, right? Divide by 2 times the 105 times the change. So that's important. Make sure you use the decimal form in the numerator. So that's 0.003. So that gives us an effective duration of 2.41 years. So 3-year bond, effective duration of 2.41 years. Notice the LOS asks us to interpret. And so what this is going to tell us is that if the yield curve shifts upward by 100 basis points, then the bond will lose 2.41% of its value. And that answers the calculate and interpret part. A couple of important notes at the bottom. Effective duration of a bond will not exceed its maturity. That probably we didn't even need to put that down there. However, there is a sentence or two in the reading about tax-exempt bonds when they're analyzed on after-tax basis. That effective duration, it may do that. It doesn't have to mathematically, but it might. So I probably know that about tax-exempt bonds. And that last one is probably important when you're asked to compute the duration of a portfolio. Effective duration of cash is 0. All right, let's work through a couple of comparisons here. So for callable bonds, the effective duration cannot be greater than that of a straight bond, right? That makes perfect sense. So as the interest rates rise above the coupon rate, the call option moves out of the money, right? So essentially then the bond is probably not going to be called anytime soon. And so the option-free bond and the callable bond are going to have identical effective durations, which means that when yields are super high, the callable bond acts identically as the option-free bond. However, when interest rates fall, the callable bond, the call option moves into the money and the bond will most likely be called. So what that does is that smashes the effective duration down, right? How about the putable bonds? Well, this is identical to what we just did, but we're going to just switch this around. Effective duration of a putable bond cannot exceed that of a straight bond. That makes perfect sense. But now we're doing the backwards stuff here. When interest rates fall below the bond's coupon rate, the put option is out of the money, and the putable bond acts like an option-free bond, so their effective durations are probably going to be extremely similar, if not identical. However, when the yields go up, the put option then is in the money, which means that the bond is likely to be put by the bond holders, so that downward potential is limited, and that just smashes the effective duration. How about this concept of one-sided duration? I think this is fairly interesting. Bonds with embedded options have asymmetrical price sensitivity. All right, let's pause and think about that. I've mentioned the word asymmetry a couple of times in the readings. Look at the second teardrop point. This explains it here. When we're in the money, the price of the callable bond has limited upside potential, right? We just talked about that. The price of the putable bond has limited downward potential. All right, so that makes sense. However, let's go ahead and look at one-sided durations. These are effective durations when the interest rates move upwards or downwards. So they're better measures than two-sided durations, especially, and this is probably super helpful in answering this LOS question, especially when the embedded option is near the money or at the money. Callable bonds are more sensitive to interest rate rises than to interest rate falls. Putable bonds are more sensitive to interest rate falls than to interest rate rises. So look at those bottom two teardrop points. Memorize those things and then attach that to the asymmetry of price sensitivity. And that has everything to do with those two pictures that we looked at in the beginning of this slide deck, with the move from positive convexity to negative convexity for the callable bond, and from positive convexity to more positive convexity on the putable bond. All right, what have we done so far? What we've done is said, hey, let's suppose that the yield curve shifts upward or shifts downward, but we know that's not the case. So why don't we look at this concept of key rate duration? Instead of saying the entire yield curve goes up or down by 100 basis points or 30 basis points like we did in that example, let's pick one spot on that yield curve and let's increase that one or decrease that one. So key rate duration measures bond price sensitivity to changes in the shape of the benchmark yield curve. Only key points, rather than the entire curve, are shifted, and they're shifted one at a time. And the reason that we shift one at a time is because we're trying to improve on the measure of interest rate risk that effective duration is. Remember, that effective duration was based on parallel shifts. Key rate duration is now going to add some value to our understanding of price and callability or putability when the shifts are not perfectly parallel. All right, so let me go back here quickly. That answers the one-sided duration and the key rate durations. All we're doing is describing here. So I think I addressed that. Yep. I remember a few moments ago I said something about duration being first derivative. So look at that tangent line. Is that red? Yes, so that's a straight line. So that's duration. That's the measure of the slope of the line at probably the current yield and the current price. But what do we know? We know that that relationship is probably not perfectly linear. There is some convexity to it, and that's the green line there. So the question then becomes, if we use duration only to try to measure and to try to estimate and understand the price-yield relationship, we're going to be wrong. If we only look at the first derivative and we ignore the second derivative, we're going to be wrong. And that's what that little rectangle box in there up the top left and the little, is that a squared box down there at the bottom right? That's the error in estimating the price based only on duration. And so in order to estimate a more accurate price, we need to estimate convexity. First derivative and second derivative. And that's why when you use duration only, you change the yield by just super small points, so you're not capturing any of that far convexity. Now, of course, some bonds have positive convexity that's fairly similar to a line, but some bonds go like this, right? Can you see what I'm doing? Some bonds have super positive convexity in which this error can be great. So sometimes the error is small for really teeny small yield changes, but sometimes it can be great. So that's why we use convexity in addition to duration. So there's a good old formula to estimate effective convexity. Notice that first one there, first arrow point. Effective convexity is the sensitivity of duration to changes in interest rates. Oh my gosh, I love that statement. All right, so the effective convexity equation looks pretty similar to the effective duration with a couple of extra variables to take into consider calculus. All right, you ready for this? Both callable and straight bonds experience similar positive convexity when interest rates are high. But the effective convexity of a callable bond turns negative when the call option is near or in the money, and that has everything to do with that picture that I showed you before. Putable and straight bonds have similar positive convexity when interest rates are low. So this slide and the previous slide here, these are just kind of summations of what I've been talking about throughout this slide deck. All right, how about a floating rate bond? Remember, an issuer is going to use a floating rate bond if they think interest rates are going to stay the same or fall, right? What's the worst thing that can happen to an issuer of a floating rate bond? That interest rates go up to, 15 to 20 or 40%, right? Then they're stuck with having to pay that high coupon payment. Well, that's why lots of floating rate bonds have a cap on it. So we'll say something like, all right, the current floating rate is 5%. We're going to cap this at 12%. So no matter what happens to interest rates, the most we can pay is 12%. Now, some have a floor on them as well. This is to attract bondholders. So if the coupon rate is, let's say the floating rate is 5%, maybe there's a floor of 2%, so that no matter what happens to interest rates, the bondholder is never going to get less than 2%. So you see that the cap benefits the issuer, the floor benefits the bondholder. So let's go ahead and work through some of these relatively simple examples. So a capped floating rate loan is a bond that pays a coupon that resets every period based on a reference rate. And the reference rate are probably LIBOR or Euribor, but there's the value of the capped floater. This is very super similar to what we've been doing all along. It's the value of the option-free bond. Of course, it has to be the value of an option-free bond because bonds are nothing more than present value of the promised payment. Now, with a floating rate bond, that promised payment is way less explicit because you really don't know what it is. I mean, you can have an idea of whether rates are going to go up or down, but it's still a present value. And then we're going to subtract out the value of the embedded cap. All right, so let's go ahead and use our interest rate tree that we did before. We've got a 3-year floating rate bond. They're capped at 6%. So what we want to do is value the capped floater and the embedded cap. So let's go ahead and do some quick math. Out at time period 3, in the old days with a fixed rate bond, we knew what that was. What was it, 105 in that last example? So it was 105, 105, 105. We knew that was going to be because it was a fixed rate bond. But now it's a floating rate bond. So based on, here, let me go back here quickly. Based on this kind of a term structure with the interest rate tree, we need that 6.5, the 5.5, the 3.5. We need that to get to what that final payoff will be. So let's start at the bottom. 103.50, there we go. 105.50, there we go. Those two are fine. But the 106, oh man, what are we saying back here? We're saying that the cap is 6%. So we're scratching that 106.50 out and saying, well, we're not going to pay 6.5% coupon. We're only going to pay 6. And so we're just going to backward induct all the way to time period 0 till we get to the 99.89. Now, feel free to pause and do all the math that you want to. If you do it, and I suggest that you go ahead and look at the LOS, calculate, so you need to do all that. Don't forget to add the coupon payment. But unlike our previous examples with the fixed rate bond in which the in which the coupon rate was fixed, so I think it was 5%, so we added 5 and 5 and 5. Here you have to add the floating rate. So there's a 5, there's a 2.50, and there's a $1.50. So don't forget that this is a floating rate bond, and so that you don't do 5 and 5 and 5 like you did with the fixed rate bond. So let's go ahead and use that equation from the previous slide. Where was I here? There at the bottom. Let's go ahead and do that. And we get 100 minus the 99.89. So there's the value of the embedded cap, 11 cents. We can do the same thing with a floor. And instead of, where am I going back here? Instead of subtracting the value of the embedded cap because the cap benefits the issuer, we're going to add the value of the embedded floor because the floor adds value. It benefits the bondholder. So let's go ahead and work through just a quick example. So 3-year floating rate, let's see, has a floor of 2%. So we're going to do the same thing. Now it's the floor, so we can live with that 106.50 out in time period 3, right? And then the 105 and then the 103. So we're going to backward induct at those rates, take present values, and then at each node, we're going to say something like, okay, let's see, 5. Well, okay, 5 is okay. Time period 2. 250, that's okay. All right. Wow, but wait a minute. At time period 1, that floating rate is 150. So we need to scratch that off and substitute the floor of the 2% coupon rate or that $2 and then continue to backward induct. And we get the 149 cents. And so the floor adds 49 cents in value to the straight bond. Keep in mind, there's no possible way that you can calculate the value of a cap or a floor floating rate bond if you don't have the understanding of the interest rate tree, the backward induction, and then the scratching out or the substitution if that embedded option moves into the money. All right, let's move on to a convertible bond. So what is this thing? This is a bond that allows the bondholder to convert the bond into shares of stock. And so this is going to be a scenario under which the bondholder is going to convert if stock price is going way up, right? Yes, I'd rather have the shares of stock because I'm limited with my return on the straight bond or this conversion option. So let's read this here. Hybrid instrument, okay, I can live with that. It gives the owner the right but not the obligation to convert the debt into equity during a predetermined period, so that's called the conversion period, at a predetermined price. So the conversion option is nothing more than a call option on the issuer's common stock. So there's a bunch of super important formulas here. Conversion price, conversion ratio, conversion value, maximum value. Hold on, let me go back here. And then market conversion price, premium, and then a ratio. So let's go ahead and work through all of these. So let's see, I'm on this slide. All right, so here's an example. All right, par value of 100, coupon 5%, conversion ratio 258, market price 110%, value 90%. So the underlying common stock characteristics 35 and 220 of a dividend. All right, so let's work through these. The conversion value is closest to, let's take the underlying share price, we're given that as 35, times that conversion ratio, so we get the $90.30 conversion value. The maximum value then is going to be not the difference, but the higher of that conversion value that we just computed, right, 90.3, and the value of the bond without the conversion feature in it, so that gives us 90.3. And then we can go through these other ones here, market conversion price, take the 110 divided by the 258, so there's 42.64. Market conversion premium, so the 42.64 is $7.64 over the current price of the share of stock, and then divide that by the share of stock, and you get the market conversion premium ratio of 2.1. So that gives you the calculate and interpret the components. And then one last thing here, downside risk and upside potential. What we're interested in using this downside risk of a convertible bond, we can take the premium over the straight value. So that's just an F over P minus 1, kind of like convertible bond price divided by the straight price minus 1. Higher the premium over straight value, less attractive the convertible bond is. So let's do just a quick example here. Market price 110, straight value of 90. So you do that F over P minus 1, you get 22.2%. Now, how about some equations here that look exactly like what we've done before, but are a little bit more complex? So this section is, what are we doing with some equations, and how do they relate to some of those equations that we had in gray boxes earlier? So I would just take a picture of this slide, put it with all of your other pictures on your phone. So value of a convertible bond, that's going to be the value of the straight bond plus the value of the call option on the issuer stock. So that's super similar to a callable bond, callable bond, not identical, but similar. But how about this one, value of a callable and convertible bond? So we're going to start with the value of the straight bond like we always do, add the value of the call option on the issuer stock, and subtract the value of the issuer call option. So we're adding something and we're subtracting something, but those two values are going to be a little different. That's why I said up in the red first box, the value of the convertible bond, it's the same process, but it's not going to be the same price. How about the bottom one, value of a callable, putable, convertible bond? So we're going to just add all this stuff, right? This is so cool. Value of the straight bond, and then we're going to sum those options in there. Value of the call option, value of the issue, we're subtracting that, and then adding the value of the put option. Let's move on to this one of these final LOSs, risk return characteristics of a convertible bond. All right, so you ready for this scenario? Let's suppose that the underlying share price is well below the conversion price. So what that means then is that this convertible bond is probably going to act an awful lot like a regular old option-free bond. So look at that second diamond point, the indented diamond point. The convertible bond exhibits mostly bond risk return characteristics, and it's described as a busted convertible. So think about what that means. When you buy a convertible bond, you're going to pay more for it, right? Because you as the bond holder have the right to convert, so you're willing to pay more for it, so you bid the price up. But if bad things happen, then your option is busted because it's out of the money, way out of the money. So here's just a super quick example, 6% coupon paying convertible bond. Let's see, stock price is $15, conversion ratio is 30, so you do the price there, 33.33. So the underlying price is well below the conversion price, a busted convertible. However, when the underlying share price is well above the conversion price, then the convertible bond looks an awful lot like a share of stock. So the convertible bond price is mainly affected by movements in the share price. So look at that last diamond point. The bond is less affected by factors such as interest rate movements and credit spreads because it's acting more like a share of stock. So this is a great exam question. When does a convertible bond act like a regular old option-free bond? When does it act like a regular old share of stock? Well, there you have the answer. And I think that takes us through a super long slide deck and a super long reading. Hopefully that all the details were good and I didn't go too quickly. My focus would be on, are you ready for this? Calculate the value of a callable or a putable bond. If you can do that one, then those things above it pretty much fall into place. Then calculate the value of a cap or a floor, which means that you can understand all that other stuff. And then don't forget about duration and convexity.